All right, good Thursday morning. We are going to finish out chapter 15, section 2 today that we started yesterday, acid-base theories. And yesterday we hit two of them. We've got to finish the last part of one of them today, and then the very last one will be done for the week. All right, so let's jump right in. Okay, so yesterday we looked at Arrhenius, who is all about ions. What do you make in water? Hydronium, you're an acid. Hydroxide, you're a base. And we also looked at Bronsted-Lowry acids and bases. So we're going to start there and we're going to review with them real quick. They were about protons. They were about hydrogens. What do you do with hydrogen? Remember, hydrogen, the hydrogen atom is just a proton and electron. Once they have lost an electron, it's just a proton. So we call hydrogen protons. So Bronsted-Lowry acid is a proton donor, gives away hydrogen. And the base was an acceptor, takes in hydrogen, give and take. If one gives, one's got to take. All right, we saw this yesterday. Here's hydrochloric acid by name, and it's going to give a hydrogen to the water. When the hydrogen's gone, we're left with chloride, and there's our friend hydronium, H3O+. So because HCl donated a hydrogen to water, the HCl is the Bronsted-Lowry acid because it donated, and the water is the Bronsted-Lowry base because it accepted. So we can be a little bit more specific with Bronsted-Lowry acids in terms of, well, how many hydrogens do you have to give away, basically? So monoprotic. If we were in class, I would be asking you what mono stands for because I know you know mono stands for one. And then you would have said monoprotic, one proton. Okay, so a monoprotic acid can only donate one proton. Examples are hydrochloric, HCl, just like you can see up above, HNO3, nitric, HClO3, chloric, any acid ever that just has a single hydrogen is called monoprotic. But we know, I hope we know that they're not all monoprotic. We have some acids that have two or three hydrogens. So let's take a look at how that works. All right, if we have monoprotic, then we have polyprotic. And again, you would know that the prefix poly means many or more than one, okay? From like when we did polyatomic ions, more than one atom. Polyprotic means you're going to have more than one proton that you can donate. Two examples we're going to look at today are sulfuric and phosphoric, okay? All right, so we're going to jump right into sulfuric. Well, sulfuric acid has two acidic hydrogens, all right? This is no different from HCl. This is no different from any of this stuff that we have looked at, all right? Here's the thing though, sulfuric acid has two acidic protons and it's going to donate both of them, but you can only donate one hydrogen at a time. That's the key. You can only donate one hydrogen at a time. So we're going to show that stepwise. Here's step one, where we've donated just one, and then we're going to look at step two. All right, so nothing new. We've got two hydrogens. We have one water molecule. This water molecule can only accept one of these hydrogens. So that's what we're going to show. We're going to donate that one hydrogen to the water. 2 minus 1 leaves us still with one more hydrogen. It's become negative because a neutral lost a positive, so it's become negative. And then water's become, again, our good friend, hydronium. So we look at this and we think, okay, all right, that seems to make sense. But I look at this piece right here. And this piece right here, this HSO4, tells me it's not finished. Sulfuric acid has not successfully gotten rid of both hydrogens because there's still a hydrogen sitting here. So how in the world do we show that? Well, we start over. We do a second step. We take the hydrogen containing piece from the first set of products here, and we do a second equation. We start a new one. And here's what that looks like. So we've taken the HSO4 and we've just started over. We've brought in a new water molecule because this water molecule from the first one's already been used up. It's already made hydronium. But remember, folks, if an acid's dissolved in water, there's going to be millions of little water molecules. There's going to be plenty to give away hydrogen to. So we just have to show, all right, we still have a hydrogen stuck to the acid and we need to get rid of it. So this hydrogen is going to leave and go to the water, and look at what we've formed. There's our polyatomic ion sulfate. That's where sulfate comes from. It comes from the complete ionization, getting rid of the hydrogens of sulfuric acid in 2 steps. And by giving that hydrogen to this water, we've made another hydronium. Now I look at sulfate and I see, oh, there's no more hydrogen. So sulfate's successful. The sulfuric acid has successfully gotten rid of both of its hydrogens, okay? Now, This is a perfectly acceptable way to show this on paper, to write this down, is to show the two-step process of how it gets rid of each individual hydrogen. But there's a little bit shorter way that can be done as well that's useful for other things down the line. All right, if you look here, here's HSO4 on the right, and here's HSO4 on the left. That's a big deal. When you have the exact same substance on the right as you have on the left in different steps, those are called spectator ions, okay? HSO4 negative is called a spectator ion. Now, if you think about movies, well, maybe not necessarily movies, but plays or sporting events or concerts, spectators are really important. You know, any athlete or performer can tell you it's more fun when you've got people watching you. You know, when you're putting on a show for somebody to watch you and to ooh and ah and cheer and, you know, whatever, to interact. Spectators are very important, but spectators aren't the most important part of the action. They're not playing the game. They're not performing the music. They're not speaking the lines. They're just responding to it. So in terms of chemical reactions, two-step reactions like this, we have spectators as well. But these spectators, they're not the most important part of the action. They don't tell you the like meat of what's really happening, the most important stuff. So what you do with spectator ions is this: we mark them out. So HSO4 is on the right on this one, and it's on the left on the second one. So I'm gonna mark them out because they're important, but they're not the most important piece of this puzzle. Once you've located spectator ions, what we do is we take our two steps and we merge them together. We add them together for one grand overall reaction, the big deal of what happened. So to do this, and again, I really hope you can see my cursor. So what you do is you just bring anything down that's not marked out. So in what I guess I'll call the first column, H2SO4 would come out. This one has been marked out, so I don't use it. Now, these are not spectators. And the reason they're not spectators is because they're on the same side. To be a spectator, you have to be on opposite sides, okay? So I bring them down together, and this will make two waters. In the third column, HSO4 is marked out, so I just bring down sulfate. And in the fourth column, we have two hydroniums. So this is what that kind of be-all, end-all reaction would look like. Sulfuric acid had two hydrogens to get rid of, so it had to have two separate water molecules, one water molecule for each of the hydrogens. When those two hydrogens are gone, we're left with sulfate, and those two waters became two hydroniums. So that's kind of like a distillation of the two steps, kind of the here's the most important stuff that happened. And that equation is called a net ionic equation. It shows the most important action in the reaction. It may not show every species like the HSO4, but it shows the most important stuff. These are the most important players in this particular reaction, okay? Now, again, it's good to be able to show the individual steps, but it's also good to be able to kind of show, well, here's the most important stuff that happened in what's called the net ionic equation. All right, let's check out phosphoric. Now, phosphoric is going to work the exact same way. It's just, I hope you're kind of looking at that. It's got three hydrogens. Sulfuric only had two. So if sulfuric had to have two steps, this one's going to have three. All right, so here's step one. We've gotten rid of one of the hydrogens, which leaves us with two still to get rid of, and one hydronium. So we see here, it's not finished because it's still got two more hydrogens. So we start again. So we take the part that still had some hydrogen and start over with it. We bring in a new water molecule so we can get rid of another hydrogen. So we take away one hydrogen from here and we still have one hydrogen left, but we've made an H3O plus. Now, if this was sulfuric acid, we'd be done because it only had two. But because this one started out with a total of three, we've still got some hydrogen we need to get rid of. So we have to go to a third step. So we start over. We take the species that still had some hydrogen on it. We bring in a new water molecule. We give that hydrogen to that water, and look at what we've got. We've got phosphate. There's where that polyatomic ion phosphate comes from getting rid of the three hydrogens in phosphoric acid and one more hydronium. All right, remember, we got to find our spectators. Who's not the most important part of this? You look on opposite sides. So I'm willing to bet, I'm hoping that you're looking and that you're finding, because there's actually two spectators here. And those two spectators are H2PO4, starts out on the right, ends up on the left. And HPO4 starts on the right, ends up on the left. Those are our spectators. They're not the most important pieces of this puzzle. So we're going to go mark them out. There goes the H2PO4 marked out. There goes the HPO4 marked out. Now we're going to take these 3 steps and we're going to merge them together for that net ionic equation. Okay. H3PO4 is the only one that hasn't been marked out, plus 1, 2, 3 waters to take care of the 3 hydrogens. Everything's been marked out except for phosphate. And then we have 1, 2, 3 hydroniums. So that's our net ionic equation showing the most important action of this reaction. All right. Now, we've called these polyprotic acids, but we can be a little bit more specific, just like we had monoprotic. Sulfuric acid, H2SO4, is a diprotic. Di, you will remember, I'm sure, like carbon dioxide means 2. So a diprotic acid specifically can donate 2 protons. And then phosphoric acid's triprotic. As I know you know, tri means 3, and it can donate 3 protons. You can't donate more than 3. Okay, so acids are either going to be monoprotic, diprotic, or triprotic. All right, and that's Bronsted-Lowry. Their acids donate hydrogens. All right, the very last definition, the last person that we have a definition for, this one's kind of out there, really and truly. The first 2 were considered traditional definitions. This one's just not like that, okay, kind of different. And these are called Lewis acids and bases. Now, Lewis is a name that you should be familiar with from last semester when you did Lewis structures, which were the pictures of molecules, like when you drew what they looked like and you drew dots to show their non-bonded electrons and you drew lines to show their bonds. This is the same guy. And because he dealt a lot with electrons and their bonding and stuff like that, he decided, okay, well, I like electrons a lot, and I'm going to apply electrons to acids and bases. And so Lewis is all about those electron pairs, those electrons that can be bonded, that kind of thing. And this is the broadest definition. Anything that has electrons can be an acid or a base, according to Lewis, okay? The other 2 don't work that way. You're either hydrogen or you're hydronium and hydroxide. That's the only way you can be an acid or a base. Not Lewis. Lewis says, hey, you got electrons, you can be an acid or a base. All right, so his acid, a Lewis acid, is any substance at all, doesn't matter what's in it, that can accept an electron pair, that has room, that has an open orbital to make a new bond. So I've got a picture here for you of some Lewis structures. Here we have hydrogen. The hydrogen ion, remember, it's just a proton, doesn't have any electrons because it's the positive says it's got rid of them, so it has room, has plenty of room for electrons. Then we have ammonia, NH3, which has the lone electron pair right here. And I've drawn this arrow to show you that hydrogen is going to be able to accept the electrons. And they're going to make this new, again, I really hope you can see my cursor. They're going to make on the right-hand side this new, I bolded it so you'd see it better, this new bond between the 2 of them. They're going to come together and make one substance. So because hydrogen is accepting that electron pair, according to Lewis, it is an acid, okay? Totally different from what the other 2 have to do with. All right, well, as we've seen before, if there's an acceptor, if there's a receiver, if there's a taker, there's got to be a giver, okay? So the Lewis acid is the acceptor. The Lewis base is the giver. The Lewis base is a substance that can donate electrons, that has some extra electrons and can donate them. So if I go back over here, the hydrogen accepted because the nitrogen gave, the nitrogen donated. So hydrogen was the Lewis acid. The NH3 was the Lewis base. Okay, if you can figure one of them out, you automatically know what the other one is. So over here, now I mentioned that this is the broadest definition, that it can apply to anything. Here's an example of that, okay? With everything that we've seen so far, we're expecting to see hydrogen. We're expecting to see hydroxide. We're expecting to see hydronium. We're expecting to see stuff like that. There's nothing like that in this picture. And this shows you that Lewis doesn't care about those kinds of things. All he cares about is electrons. What's happening with electrons? So in this one, we have BF3. Boron has 3 valence electrons, so it can get away with just making 3 bonds. We're expecting an octet, 4 bonds, but boron's kind of different, so it can get away with that. Here we have fluorine, totally full. It's got its full octet, 8, so it's got some extra electrons. Boron has some open space. So fluoride's going to donate those circled electrons right there to that open spot on boron and make that new darker bond in this new substance. Okay. So because fluorine is donating those extra electrons that it has, it's considered a Lewis base. Lewis is just out there. It doesn't mesh very well with the other two, but it's one of those theories that they want us to learn about. All right, so to wrap this up, to review, going back to yesterday and today, section 2. Arrhenius, what do you make in water? He says if you're an acid, you will produce hydronium when you're dissolved in water in solution. If you're a base, you're going to produce hydroxide. Bronsted Lowry, they're all about protons, hydrogen. What do you do with them? You're an acid if you donate protons, if you give protons away, and you're a base if you take them, if you accept them. And again, these two are the traditional definitions. When people think about acids and bases, these are the two that they think about. Then we have Lewis, who's about electrons. He says an acid is anything, doesn't matter what's in it, as long as it's got electrons. Lewis acid is anything that accepts electrons, and a base is anything that donates an electron. And again, this is the broadest definition because pretty much everything has electrons, okay, or has the ability to bond. All right. So now that you've gone through this, head back over to Google Classroom and do the very short little assignment that goes with today. It's Thursday, so this is our last lesson of the week. Remember, on Friday is kind of a makeup day or get caught up day. So if there's anything from this week that you didn't get done Monday through Thursday, tomorrow's the day to kind of get caught up on that as you would. If you are getting caught up on stuff on Friday, please try to have it done by the end of Friday, because Saturday is when I'll take care of grades and getting grades put in the computer and everything, and get everything caught up and up to date. So hope you have a good weekend, and we will come together and learn some more on Monday. So have a good weekend.